There's a blind man who can see using his tongue, a deaf woman who hears through her skin, and a guy who literally feels color like a human radio tube because of an antenna planted directly into his skull. These aren't superheroes. These aren't science fiction characters. These are real living people. And the scientists studying them think they're accidentally showing us what the next version of the human species looks like. But here's the thing nobody's saying out loud. This isn't even about disability anymore. Okay, here's the thing nobody tells you about your senses. You don't actually see with your eyes. You see with your brain. Your eyes are just cameras. Wet, squishy, kind of disgusting cameras. The real magic is happening upstairs, where your brain takes a stream of electrical signals, billions of them per second, and goes, cool, that's a chair. That's my friend. That's a bear. Run. Here's where it gets strange. Your brain doesn't care where those signals come from, not even a little. If you can route the right information into the brain through any channel, the brain will figure it out. It will adapt. It will rewire. It will build a whole new internal experience from scratch. That idea has a name, sensory substitution. And once you actually understand it, not just the surface level version, but the deep version, you will never think about human potential the same way again. So let's go deep. We have to start with Paul Baccarita, neuroscientist, Spanish American, born 1934, and in the 1960s, one of the most genuinely radical thinkers in all of science. Here's a bit of context that makes his latter work make sense. In 1958, his father Pedro suffered a severe stroke, paralyzed on one side, couldn't speak. Doctors said he'd never recover. His brother George, who was a psychiatrist, refused to accept that, and spent years doing intensive rehabilitation work with Pedro, who eventually recovered enough to live a full life, teach university, go hiking, and travel. Paul was a medical student at the time, and that experience planted a seed. Maybe the brain is way more flexible than anyone thinks. So he went into neuroscience and started testing that idea. And in 1969, this is the moment that matters, he published a paper in the journal Nature that is now considered one of the first pieces of experimental evidence for neuroplasticity in history. Here's what he did. He built a chair, a dentist-style chair with a grid of 400 vibrating tactors, tiny pressure points built into the back. He connected the chair to a camera. Whatever the camera saw, the chair translated into a pattern of vibrations on the sitter's back. He then had blind volunteers sit in the chair and attempt to interpret what they were feeling. At first, confusion, random buzzing sensations, nothing coherent. But then over time, something clicked. People started perceiving shapes, objects, movement. One blind participant was even eventually able to detect a ball rolling toward them and track its trajectory. And here's the line from Baccarita that broke every neuroscientist's brain when they heard it. We don't see with our eyes, we see with our brains. The trials in 1969 are now formally recognized as some of the first experimental evidence that the adult brain can rewire itself based on new sensory input. The scientific term is neuroplasticity, and at the time it was a genuinely controversial idea. The dominant view was that the adult brain was fixed, hardwired. You were born with the circuits you had. Baccarita's work said, no, it's not. So Baccarita kept going. He refined the idea over decades, and his most famous device, the one he's best known for, came from a deceptively simple insight. The tongue has one of the highest densities of sensory receptors anywhere in the human body. It's incredibly sensitive, and it's naturally coated in a thin electrolytic solution that makes electrical contact easy and efficient. So he built an electrode array, a flat grid of tiny electrodes, mounted on a dental retainer that sits on the tongue, connected to a camera mounted on a pair of glasses. The camera captures visual information. The electrodes translate it into precise patterns of gentle electrical stimulation on the tongue. The tongue sends signals to the brain, and the brain interprets them as vision. He called it the brain port. Now, at first, it's chaos. People describe it as random tingling, white noise on the tongue, meaningless. But here's where it gets genuinely extraordinary. After just a few hours of training, people start perceiving shapes, edges, contrast, depth. And when researchers did brain scans on people using the device, here's what they found. Are you ready for this? The visual cortex was lighting up. Not the touch processing area of the brain, not the somatosensory cortex where tongue signals normally go, the vision department. The brain had looked at the information coming from the tongue, recognized it as visual data, and routed it to visual processing. It had reorganized itself on the fly. Baccarita died in 2006. Fittingly, he collapsed while mountain climbing in Bogota, Colombia, still adventurous until the end. But his company, Wicab, carried his work forward. The device is now called the BrainPort Vision Pro. It is FDA approved. There are blind people using it today, right now, to navigate the world, seeing through their tongue. That is not a metaphor. That is a factual statement. Just to sit with that for a second. A blind person is perceiving the visual world through their mouth. The brain took electrical signals from their tongue, and filed them under vision. That's the most cyberpunk sentence I've ever said that is also a peer-reviewed scientific fact published in Nature. Okay? So let's go deeper. So if Baccarita established that the brain could reroute vision through the skin, the natural next question is, okay, how far does this go? Enter David Eagleman, neuroscientist at Stanford, CEO of a company called Neosensory, author of a book called Wired, which is one of the best science books written in the last decade, and I will die on the hill. Eagleman had a question that went beyond restoring senses. He asked, could we give humans genuinely new senses, not replacement senses, additional ones, new channels of information that evolution never gave us? So he built a vest, a wearable torso garment embedded with an array of approximately 40 small vibrating motors, electromechanical actuators, controlled by a small computer. The system works like this. A microphone picks up sounds from the environment. An algorithm processes those sounds, encoding their frequency, amplitude, and timing. That information is then converted into patterns of vibration across the torso. The goal was to see whether a person who had never heard sound could learn to feel it and eventually understand it. He and his graduate student, Scott Novitz, began testing it in 2013. They named it the VEST, for Versatile Extrasensory Transducer. The early results were striking. Deaf and hard of hearing participants trained with the vibrotactile patterns derived from sounds showed significant improvements in identifying environmental cues, spoken words, and musical elements, with recognition rates climbing from near chance levels after a few weeks of training. And, just like Baccarita's tongue results, brain scanning showed that the auditory cortex was processing the tactile vibrations. The brain was hearing through the skin. But here's Eagleman's bigger point, and it's the part I want you to really hear. He doesn't see this technology as just a rehabilitation tool. He thinks the vest and devices like it represent the beginning of deliberate sensory expansion. Right now, his company Neosensory has shrunk the technology from a vest down to a wristband that's already on wrists around the world. He tested an earlier version at Google's offices, tapped into the building's LiDAR system, strapped the vest on a blind participant named Alex, and Alex was able to perceive the location of people moving around him in 360 degrees. He could see in 360 degrees, Eagleman said, going from blind to Jedi. And that's what technology we have today. So here's the concept I need you to lock in. Eagleman talks about something called the Umwelt. It's a German word coined by the biologist Jacob von Uexküll in the early 1900s. It means the specific slice of the universe that an animal's senses allow it to perceive, its subjective sensory world. A dog's Umwelt is dominated by smell. It can detect scents at concentrations 100,000 times lower than humans can. A bat's Umwelt is built on sonar. A shark can detect the electric fields produced by the muscles of nearby prey. A mantis shrimp has 16 types of color receptors compared to our 3, and can see wavelengths we don't have names for. Every creature lives in its own sensory bubble. Eagleman's argument is humans assumed our bubble was natural, fixed, the product of evolution and nothing more. What sensory substitution is showing us is that it's not fixed at all. The brain is a general purpose processor. The eyes are just one type of camera. The ears are just one type of microphone. The brain doesn't care what inputs it gets. It builds an experience from whatever arrives, which means the bubble can be expanded. So, here's where things get real interesting, and honestly a little weird. Because while the scientists were running trials, a different group of people decided not to wait. Neil Harbison was born in 1982 in Northern Ireland, raised in Catalonia. From birth, he had a condition called achromatopsia, complete total color blindness, not red-green color blindness, which affects about 8% of men, complete achromatopsia. His entire visual world was grayscale, shades of gray from birth. In 2003, he attended a talk on cybernetics by a student named Adam Montandon at Plymouth University. They started talking afterwards, and what came out of that conversation eventually changed both their lives. They developed a device, initially just a camera mounted on a headset, connected to a laptop, that could detect the dominant color in front of Harbison and play a corresponding musical note through headphones. Red was mounted to one frequency, blue to another, green, yellow, purple, each had a sound. At first it was just sounds, external sounds. He had to constantly decode them the way you decode a language you're learning. But something changed after months of training. He stopped hearing colors. He started experiencing them, not as sound anymore, as a new, unnamed sense. He started dreaming in color sound. He developed a color preference. His favorite, he says, is infrared. He started recognizing people by the frequencies of their faces. The particular frequencies, their skin tone, and hair color produced in his antenna. And here's the beautiful, surreal detail. He said that listening to a Mozart symphony is like watching a living light show, because the notes activate his color sense simultaneously with the musical experience. Over the following years, he worked with engineers to implant the system directly into his skull, a chip bonded to the bone, transmitting color vibrations by way of bone conduction, with an antenna extending forward from the back of his head. No wires, no laptop, no headphones, just a sense built into him permanently. When he tried to renew his UK passport in 2004, the passport office rejected his photo because he appeared with an electronic device on his head. He wrote back explaining that he identified as a cyborg, that the antenna was not a device but a body part, and that they were photographing him with an organ, not equipment. After months of correspondence, his passport photo was accepted. That made Neil Harbison the first person to be officially recognized by a government as a cyborg. He now appears in his passport photo with the antenna, which remains one of the most quietly extraordinary facts in recent human history. He went on to co-found the Cyborg Foundation with his childhood friend, dancer and choreographer, Moon Rebus. Moon Rebus had a different idea. In 2013, she had seismic sensors implanted, originally in her arm, later moved to her feet, wirelessly connected to online seismograph networks. The device activates wherever an earthquake occurs anywhere on Earth. Any earthquake, even a magnitude 1.0 on the Richter scale. She experiences at least 2 vibrations per hour. The 2015 Nepal earthquake, magnitude 7.8, woke her in the middle of the night with powerful vibrations. She's incorporated this sense into her work as a dancer and choreographer. One piece, called Waiting for Earthquakes, has her stand perfectly still on stage until seismic activity is detected, then move in accordance with the earthquake's intensity. The Earth is the choreographer, she is the interpreter. Her seismic sensors have allowed her to feel moonquakes, seismic activity on the moon, which she describes as allowing her to be physically on Earth while her feet fill space. In 2013, she was recognized by Guinness World Records as the first biohacker to implant earthquake sensing technology. These aren't science fiction characters. These are real people living their daily lives with senses that don't have names yet. I want to pause on that for a second. Moon Rebus feels every earthquake on the planet in real time, every one, at least twice an hour. She turned it into choreography. That is either the most profound art project in human history, the most extraordinary scientific experiment ever conducted in a person's body, or both simultaneously. I genuinely don't know how to categorize that, and I find that very exciting. So here's the question that I couldn't stop thinking about when I went down this rabbit hole the first time. How fast does this actually happen? Like, if you strap a camera to someone's tongue, how long before they actually see? The answer is shockingly, almost uncomfortably fast. Studies with brainport-style devices showed meaningful perceptual results in as little as 1 to 2 hours of training. Real proficiency develops over days to weeks. People go from random tingling to perceiving shapes, tracking objects, and navigating environments in a time frame that should feel impossible for something this radical. And here's the part that makes neuroscientists genuinely lose their minds. When you take the device off, the rewiring partially persists. People who train with tongue display devices report enhanced ability to interpret tactile information even without the device. The brain's new mapping doesn't simply undo itself when the hardware is removed. Michael Merzenich, one of the founding figures of neuroplasticity research, winner of the Kavli Prize, widely called the world's leading researcher on brain plasticity, spent decades mapping exactly this phenomenon. He and his colleagues demonstrated that the brain's sensory maps are not fixed at birth. They're not fixed at adolescence. They're not fixed at any age. They are constantly updated, competitive, dynamic. The cortex is basically a living document that keeps getting rewritten based on what information comes in. One of his landmark findings, when he cut the median nerve of a monkey's hand, the nerve that delivers sensation to the middle of the palm, and then remapped the brain 2 months later, the cortical territory that previously represented that part of the hand hadn't gone quiet. It had been colonized by neighboring neurons. The brain refused to waste the real estate. That principle, the brain's refusal to leave territory idle, is the same reason the visual cortex of the blind gets recruited for touch and hearing. The same reason Baccarita's tongue signals ended up in the vision department. The same reason Moonriba's seismic sense feels like a genuine sense and not just a vibration. The brain finds a home for whatever you give it. Merzenich put it this way: neuroplasticity exists from cradle to grave. The ceiling on human perception isn't set by evolution, it's set by the information we give the brain access to. That's a staggering sentence. Let it land. Which brings me to the question I've been building toward this whole video. If the brain can learn to see with its tongue, hear with its chest, and feel earthquakes with its feet, what does that mean about the 5 senses we were all taught? Most of us grew up learning we have 5 senses: sight, hearing, smell, taste, touch. That framework is Aristotle's. From approximately 350 BC, we have been walking around with a 2,300-year-old model of human perception in our heads. It's not wrong, exactly, but it is wildly incomplete. Modern neuroscience recognizes somewhere between 9 and 33 distinct sensory systems, depending on how finely you categorize them. Here are just the obvious ones that didn't make Aristotle's list. Proprioception, your sense of where you are in space without looking. Close your eyes and touch your nose. That's proprioception at work. It's why you can walk upstairs without watching your feet. It's why you can catch a ball without it, movement becomes nearly impossible. The vestibular sense, balance and spatial orientation, managed by structures in your inner ear. Without it, you can't tell which way is up with your eyes closed. Thermoception, temperature, distinct from touch. You have specialized receptors for heat and cold. Nocioception, pain, also distinct from touch. Its own receptor system, its own pathways to the brain, its own cortical processing. Interoception, the sense of your own internal body states: hunger, thirst, your heartbeat, the urge to breathe, the feeling of needing to urinate. These are all sensory signals processed by the brain, generating subjective experience. Disruptions in interoception are now linked to anxiety disorders, depression, and eating disorders. It turns out that knowing what's happening inside your body is a sense too, and when it breaks, things go seriously wrong. So, the scientific definition of a sense is any channel through which the brain receives and interprets information about the world or the body. By that definition, the vest is a sense, the brainport is a sense, Moonriba's seismic sensors are a sense. A future device that feeds GPS coordinates as a felt direction is a sense. a hypothetical chip that streams real-time air quality data as a skin sensation is a sense. There's no theoretical wall. Eagleman has pointed out that the brain has far more processing capacity than we currently use for perception. We've been running 5 inputs on a machine that was built for potentially dozens. What happens when you give it 50? We're starting to find out. Here's where we are in 2026. The BrainPort Vision Pro is an FDA-approved medical device. It's not experimental anymore. It's a product you can get. Blind people are using it today. Neosensory, David Eagleman's company, has shrunk the vest technology to a wristband. It's in commercial production. Deaf and hard of hearing people are wearing it. Neuralink implanted its first human patient, a 29-year-old quadriplegic named Nolan Arbog in January 2024. By early 2024, he was controlling a computer cursor with his thoughts, playing chess, browsing the internet, learning French and Japanese. As of 2025, there were 12 trial participants with over 15,000 cumulative hours of usage logged. The UK's first patient received an implant in October 2025 at University College London. Over 45 separate brain-computer interface trials are underway globally across multiple companies and research institutions. The cochlear implant, which converts sound to electrical signals delivered directly to the auditory nerve, bypassing the ear entirely, has been implanted in over 1 million people worldwide. It's been around since the 1970s. We've been doing sensory substitution for 50 years. We just didn't call it that. What's different now is the intention behind the technology. For most of the history of sensory substitution, the goal was restoration. Give something back to someone who'd lost it. That's an obviously worthy goal. But the researchers who started with restoration have ended up something philosophically much wilder. They've ended up with a question: why stop at restoration? Eagleman has pointed out that the brain doesn't care whether you're restoring a lost sense or adding a new one. The biological mechanism is identical. The brain adapts, it integrates, it builds experience from signal. If the delivery mechanism exists, if you can build a peripheral device that captures information and routes it to the nervous system, the brain will handle the rest. The question has shifted from can we do this to what do we want to feel? I want to be honest about what we don't know, because this channel doesn't pretend there aren't open questions. First, the long-term picture. Most studies of sensory substitution devices measure outcomes over weeks or months. We have relatively limited data on what happens over years or decades. What does sustained sensory rewiring do to the brain across a lifetime? We don't fully know. Moon Rebus actually removed her seismic sensors after approximately 7 years, choosing to end the experiment on her own terms, describing it as a personal decision about her relationship with the sense she had developed. That's worth noting. Living with a new sense for 7 years and then choosing to let it go is itself an extraordinary data point. Second, access and inequality. A world where some people can afford to augment their senses and others can't is a world with a new axis of inequality layered on top of all the existing ones. A society where cognitive and perceptual enhancements is available to the wealthy and not to everyone is a deeply ethically complicated place. Legal scholars at institutions like the University of Sydney are already working on this. Third, identity. When Neil Harbison says he no longer feels 100% human, when he identifies as a trans species, that's not a metaphor or an artistic statement. He means it literally. His phenomenal experience of the world is genuinely different from that of any other human being who has ever lived. What does personhood look like in a future where the sensory interface to reality is customizable? These aren't small questions, but they're not reasons to stop. They're reasons to be thoughtful while continuing. Look, when I first read about Paul Baccarita's chair experiment from 1969, I had to do about 6 separate Google searches to confirm it wasn't an urban legend. A man in the 1960s built a chair that let blind people perceive visual information through vibrations on their skin, and the visual cortex lit up on brain scans. That was 1969. Here's what I want you to take from this. Your brain is not a finished product. it's a platform. And for 300,000 years of human history, we've been running the same 5 apps on that platform that our ancestors had. What sensory substitution research is showing us, slowly, paper by paper, trial by trial, implant by implant, is that the platform is way more capable than the apps. The brain can learn to see through skin, hear through touch, feel a planet move under someone else's feet. It can do all of that. We just have to figure out what to build. And right now in labs and garages and studios around the world, people are building. Drop a comment with the sense you'd want most if you could add one. Mine's infrared. I want to see in the dark like a cat, and I also understand why my cat stares at walls for no reason. Apparently they're watching infrared signals, which is something I learned while making this video and have not recovered it. Subscribe if you want more videos that feel like finding a secret door in the universe. And check out my links below. And hit like if you enjoyed this video.